Welcome to the Apron Academy. This video is specially designed for the dietitian in training, also known as the RD-to-be. In this video, we're going to be talking about manganese. So manganese is kind of not really all that popular, but how you can find it, it has several valence states. So one of those is Mn3+, another is Mn2+, and even Mn7+. So because of the many valence states, it's able to function in redox reactions. It has signaling, catalytic, and regulatory functions as well. So where can we find it? We can find it in nuts, seeds, unrefined cereals, tea, leafy vegetables, but there are low levels of manganese in meat, seafood, and dairy products. So in many of my videos, I talk about the absorption mechanism, but actually with manganese, it's not really known, and it actually depends on interactions with other dietary components. So there could be an inhibition of manganese absorption caused by high iron and or zinc. So not really known, kind of depends on other things. And following absorption, manganese is thought to either bind to alpha-2 macroglobulin, so alpha-2 macroglobulin, and it can be bound to this for delivery to the liver, and because it can be oxidized to Mn3+, it can bind to transferrin, suggesting that its uptake occurs through receptor-mediated endocytosis. But again, don't really know the whole pathway. When it's excreted, most of it's lost in the feces, not in the urine, and when manganese is transported to the liver, it rapidly enters the mitochondria for incorporation into SOD. So we'll talk about superoxide dismutase, which helps get those free radical scavengers, and it's sequestered into lysosomes from where it's actively transported into the bile. Okay, so let's now talk about manganese's primary functions. So functions with superoxide dismutase, or SOD, and free radical protection. So manganese-dependent superoxide dismutase, which again, SOD is important for being a free radical scavenger. When manganese-dependent superoxide dismutase is a part of the body's defense against reactive oxidative species. So free radicals can damage our DNA, proteins, lipids, and alter cellular function. So SOD catalyzes the reaction in which superoxide is removed. So intra and extracellular SOD can use copper and zinc, but only mitochondrial SOD uses manganese. However, if we do have a manganese deficiency, we can still use the copper and the zinc. So that's not necessarily manganese specific. However, if you don't leave this video remembering anything else, remember this. There's only one enzyme that's specific to manganese. It's this, glycosyl transferase. This helps form glycosidic linkages for the formation of collagen, and we've discussed before that collagen is super important, so we need this glycosyl transferase to make that be that enzyme specific to manganese. So what happens if we don't have enough? So some deficiency symptoms include reduced growth, abnormal bone formation, impaired glucose tolerance, poor reproduction, and malformations in offspring. So it could indicate that there's more of an importance of manganese in utero production. But there can also be a toxicity. So patients with liver failure are at higher risk as liver excretion in bile maintains that homeostasis of manganese. So typically, we may not have a manganese toxicity. It only happens secondary to liver failure because manganese can accumulate in other organs such as the brain and could lead to neurologic abnormalities. So some of those signs and symptoms of toxicity include insomnia, headache, forgetfulness, mood changes, compulsive behavior, reduced response speed, rapid hand movements, and gait disturbances. So this was a quick little video showing that manganese is super important. If you found this video helpful, please like and subscribe and share this video with others. I'll see you next time.